So this tutorial is going to be on using gpvdm to simulate PL or photoluminescence. PL is a very interesting experiment because what you do is you get a laser or some optical source and you photo excite your device, and then you measure what photons are then emitted from your device and so what wavelengths of photons are emitted from your device. And it's a very interesting technique because it can tell you things about recombination, the density of states, and sort of how efficient your device is at emitting light. You can learn quite a lot of information from photoluminescence. So what we're going to do is in this is we're going to use gpvdm to simulate PL, and we're going to effectively simulate it being pumped with a laser, and then we're going to watch the spectrum of photons that are emitted from the device. So firstly, to do this, we're going to make a new simulation. Now, for this, I could choose any type of device simulation, but I'm just going to choose a P3H PCM OPV device, just because it's got a particularly interesting density of states. So we're going to make a new solar cell, and we're going to save it on the desktop as example. And there we go, we get our solar cell. So at the moment this is just a standard solar cell, and this could be a perovskite device, it could be any device that you're interested in. So if we just run a simulation as usual, we'll get out of it some type of a JV curve. So there's the JV curve, and you can see, you know, JSC and VOC and fill factor and all that is there. So what we're going to do now is we're going to turn off the lights. We're going to have it in the dark. So we set the light intensity to 0, and now our cell's in the dark. What we then do is we go to the electrical parameters tab, and this is the active layer, this one with a little blue tab, the P3HT PCBM layer. I'm going to turn on photon emission, and we get an edit button appear here. So we just click on edit, and what we have here is we then have 5 different parameters, and these parameters can be between 0 and 1. So if we look, and I'll explain what these are in a sec. So if we look at sort of the band diagram of a typical organic semiconductor or disordered material, it looks like this. So if we zoom in on that, we can see that there's 3 charge carriers here. So this is energy up here, and this is the density of states. We've got 3 charge carriers here, which are electrons. We've got 3 holes here, and these are the trapped states. We've got trapped holes here, and we've got trapped electrons here. And there's effectively sort of 4 processes that can, or 5 processes that can go on. You can have electrons being captured into the trapped states, or you can have electrons being recombining with trapped holes, or you can have 3 holes trapping into trapped states, or you can have 3 holes recombining with trapped electrons. You can also have 3 electrons recombining with 3 holes. So there's 5 processes there. And what this window does is it basically assigns a value between 0 and 1 to each one of these processes and at how efficient it is at emitting photons. So if the value is 1, it means the process, for every transition that happens, you'll get 1 photon out. So every electron that recombines every hole, you'll get 1 photon out. And if the value is 0, you'll get none, and 0.5 is somewhere in the middle. So what we're going to do is just set all those to 1.0. Obviously, if you had your own experimental data and you had some more information about the device you're modeling, you'd adjust these parameters until your PL spectrum basically fit your data. So we're going to close that and close that window, and if you notice, all of a sudden now we get blue photons emerging from our device. The blue doesn't really denote anything particular, it's just the colour that I chose for the arrow. Then we're going to flip the simulation mode, so instead of being in the JV curve, we're going to simulate PL. So we just click on PL and just click run, and it's done the simulation. So if we click on output, what we get is we get 5 files. So we get emission, free electron to free hole, emission, free electron to trapped electron, emission, free hole to trapped hole, and emission, trapped electron to free hole, or free hole to trapped electron, whichever way I want to look at it. And then we get 1 more there, and hang on, the final one is this one, which is emission tot. And we'll look at emission tot, which is basically the total emission spectrum from this device after being pumped. And you'll see there's 2 bands. There's 1 band here and there's 1 band here. The first band is the band you'd probably see experimentally up here, this high energy band. So round about sort of 1 EV. This is, I guess, sort of the wavelength you'd probably see devices emit at that have been pumped by a laser. And effectively, this shape is due to the shape the electrons and holes occupy in the density of states. And this is all caused by effectively free electrons recombining with trapped holes and free holes recombining with trapped electrons. This much deeper band that you can see down here, you probably wouldn't observe experimentally, but it's due to effectively relaxation of electrons to trapped electron states and relaxation of holes to trapped hole states. And so that's all very interesting. If you look in each one of these files, you'll be able to see sort of the individual components that add up to produce this total spectrum here. So there's another one, and there's another one. And if you get something like Origin, plot all these files, you can see how they join up to make this total spectrum. So that's all very interesting. Now, what we usually do when we simulate organic devices, we assume, or many other types of devices, we assume a exponential tail of trapped states, so that the traps are basically exponential. But there's no particular reason why they should be exponential. I mean, there's evidence suggests they are, and it fits experimental data quite well. But there's no reason we have to have an exponential there. So what we can do is we can flip this option here, which says DOS distribution. We can change this from exponential to complex. And now, rather than using these parameters here, so electron tail slope, hole tail slope, all these parameters to define the density of states, we've got a bit more freedom by clicking on this button. And here we can actually edit the density of states. So we introduce Gaussians into our device, or we can have a mixture of Gaussians and exponentials, however we want. So here we've just got two Gaussians. And there's a bit of an exponential down here. So what we can do is we can change the position. I think that's position. We can change the position of the Gaussian. So we can move it down energy a bit. So that pops down energy, maybe a bit more. Maybe bring up the magnitude of that exponential because it's very low. Maybe a bit more, maybe 21. And you can see you can sort of add, so that's for the LUMO, then you can edit the HOMO down here, so maybe decrease this a bit. So you can build your own density of states effectively. You can add in as many functions as you want. So now we've done that, we can just run another PL simulation, and now it's using that complex density of states, and we can look again at the PL, and you see the PL distribution's changed a bit. Or if you want to go back and make it a bit more sort of an extreme density of states, we can broaden these out, these Gaussians out to be super broad, and we can then run the simulation again. And we can basically see what impact that would have on your density of states. And so that's look, you probably wouldn't observe that experimentally. You probably would have, I don't know, this peak here probably wouldn't be so dominant. So you can go back again and reduce some of these terms here as you like. So what this enables you to do is effectively correlate, so I'll get the density of states up again, the density of states to the PL emission from a real device. And this isn't just sort of, it should be noted that this is effectively simulating the PL emission from the whole of the device. So it's a full 1D model of it. The final file that's worth looking at is this file called emission XYZ, and this plots basically the number of photons emitted as a function of depth in the device. So your pump light's coming from the top, so you'd expect there to be more photons absorbed at the top, therefore more emission, more PL emission, and that's what's shown. We sort of have more PL at the top of the device, which is that bit there corresponds to the top of the device here, and this bit here which corresponds to this bit here. And this sort of profile, I guess, follows pretty much the optical profile that the excitation laser takes in the device. So that's it really. That's just a quick tour of how to do PL simulations with gpvdm. I hope you found this very useful.